This is a quick video about spacetime or Minkowski diagrams. And in order to really understand this, I just want to review normal old space versus time diagrams in regular old Galilean relativity. One thing we're going to do a little differently here is I'm going to put position on the horizontal axis. The reason I'm going to flip the axes is because later we're going to look at something called world lines, and it's just sort of easier to see if the axes are flipped. The other thing I'm doing, which is a little different, is instead of just plotting t, I'm plotting ct. And the reason for that is c is such a big number that if I were to draw the trajectory of things in terms of the speed of light, which I'm going to have to do in order to see these effects, everything would have such a small angle that you wouldn't really be able to see anything. So just think of this as scaling. In fact, what theoretical physicists do is theoretical physicists just say c equals 1. And you might say, what do you mean c equals 1? Well, they just redefine their units in a way that c is 1, and then they really are just plotting x versus t. They don't even need the c there because it's just a 1. Okay, anyway, let's review what it looks like to plot things in this normal space-time. Okay, so here I've got a rocket ship. The rocket ship starts in one place at time 0, so we'll just call this 0, and then it ends at some other place. So what are some things I can do? Well, I can calculate the speed of the rocket, and I do that by basically saying how far it went divided by the time. So here it goes 1 unit in x and 4 units in t. Now, one thing to keep in mind is if you look at this, you're like, that slope sure doesn't look like 1/4. You're right. That's because, again, I'm plotting ct versus x. So this is actually a slope of 4. In other words, things are reversed. I know it's annoying, but it'll pay off later, I promise. Okay, now let's think about it from the rocket's point of view. From the rocket's point of view, it considers itself at rest. In other words, I said the velocity of the rocket relative to the ground here, but the velocity of the rocket relative to the rocket is 0. And that means that as far as the rocket's concerned, its measurement is that it starts at 5 and ends at 5. And so therefore it's 0. This line, this is the world line I was talking about, that's called the rocket's world line. And that actually sets up a way for the rocket to measure position because that is what has changed. In fact, I can make a grid for the rocket by just adding a bunch of those lines, the same way that I made a grid for a stationary observer by adding a bunch of vertical lines. Well, okay, if I want to look at the rocket's grid lines, the cost of it having a velocity is that those grid lines are now slanted. Okay, so the rocket's world line is at x prime equals 5. Okay, now how do they measure things around them? How is that different? Well, let's plunk an event A here. And according to someone who's in this frame of reference, in order to get from this rocket to A, they have to go over 1 and up 2. So they perceive this to be delta t equals 2 units up and x is 1 unit over. That's according to someone with the horizontal grid. But think about it from the rocket's point of view. The rocket also goes up 2 units, so up 2, but then the rocket actually measures from its grid line, so it actually goes less. So delta x prime is less than 1 and delta t is still 2 because the rocket had to go up 2, but then it only goes over a little bit. So there's nothing really amazing going on here. You say, well, yeah, the rocket thinks point A is moving relative to it, and so after a certain amount of time, you have to adjust things based on this familiar formula. One thing to keep in mind, though, is that let's say we let A move. If A is moving, how do they measure the differences in velocities? Well, we can just take derivatives. And one thing to think about is that the velocity of A prime, so how does the rocket see if A is moving? How does the rocket measure that speed? Well, you just take a derivative on x. And if you do that, you end up with dxa dt. So that's just whatever someone in the square grid measures. And then minus vt, well, there's just a t. V is constant. They're moving at constant speed relative to each other. And so you end up with that. And then what if you want the acceleration? Well, you take the acceleration. And this is actually the interesting thing that I wanted to point out. In Galilean relativity, people moving at different speeds disagree about the velocity of objects. They disagree about the position of objects, but they absolutely agree on the acceleration of objects, and that's very important. Very important. That means that forces are invariant. People in different inertial reference frames, not accelerating, will measure the same force. So you can use Hooke's law no matter which frame you're in. And here I've just shifted it so that I could say, look, the rocket's frame is equally valid. Let's make the rocket's frame the rectangular grid. And now that other frame we were looking at before, now that has the slanted lines. The rocket still goes up 2 and over a little less than 1. And this guy still goes, he goes he still goes up 2 and over 1. It's a little harder to see there, but you'll take my word for it. Okay, great. So now we have in Galilean relativity, F equals ma is invariant. Now we want to start mixing it up with Einstein. And Einstein has, this is the kooky one that messes everything up. C is invariant. Let's see what that means. Okay, here's a light ray. And the light ray has a slope of 1 because my axes are in terms of CT. So it goes C meters in T seconds. Okay, so let's make our rocket person again. So this time their slope's a little different. They go up 3 and over 1, but that's the world line of that person. So let's make measurements of where this thing is, this light ray, okay? And if you look in the rectangular frame, it's 1 by 1 and 2 by 2 and 3 by 3. That looks perfect. Now, if you look at it from the CT frame's point of view, from this guy's world line, so here I've drawn his slanted axes, this is actually a bit of a problem, because if you go up 1, it's less than 1 over. That means that this person is measuring a different speed for the speed of light than the other person is, and according to Einstein, that's not allowed. So you might say, oh, that's a problem. That means that we can't apply Galilean relativity like we did before. But you might say, hey, look, this is actually not a big deal. I've heard of this thing called Lorentz contraction. Maybe we just need to draw lines that are closer together. In other words, somehow the distances change, and then we can leave the time axes alone. So you say, okay, lengths appear different to different observers. This maybe is like Lorentz contraction. I don't know. There is a significant problem with solving the problem this way. Now, notice we have kind of solved the problem. We go over 1 and down 1. In both frames, the speed of light is 1. I'm going to show you the problem, though. What if I change the direction of the light ray? In other words, boing, it hits a mirror. It hits a mirror. And when the light is going this way, I go up 1, over 1, up 1, over 1, up 1, and it's all good. When the light goes the other way, let's just trace it up here. When the light goes the other way, I go over 1, up a half. Uh-oh, that's not good. Over 1, up a half. In other words, depending upon which way you're going, the speed of light has different speeds. That is clearly not satisfactory. What we're going to end up having to do is we're going to have to abandon our vertical tick marks as well. We were already okay abandoning these guys. Now what I've got to abandon, I'm sorry, I said vertical, I meant horizontal. Now what we've got to abandon is these two. In other words, what we're going to do, just like we made our vertical slanted, I'm going to have to slant the horizontal too. And you might say, what does that buy you? Well, look, it buys me this. If I slant the horizontal, then I go over 1, up 1, over 1, up 1, over 1, up 1. And when I go the other way, over 1, up 1, over 1, up 1, over 1, up 1. So long as I slant both axes, apparently I can fix this problem. Let's clean this up because there's a lot going on here. Okay, I've made one set of tick marks for the slanted axes. And you can see that in both frames, the speed of light is 1 over 1. In other words, it has a slope of 1. Now, what happens if I increase the speed of my world line person? Let's see what that looks like. I have to shift all the axes. Okay, but notice it's still 1 by 1. I just have to, as I increase the speed of this person, this world line person, as the relative speed increases, I have to slant the axes even more. So that's the downside. Let's go back to where we were before. Okay, and now let's make one other question. So notice this is what we want to say. We want to say, look, here I go over 1, up 1, but there's actually no rule that says that has to be 1. What if I increase the density of my tick marks? In other words, the thing that we actually don't know, okay, the angle is right, but I don't know if this is meant to be x prime equals 1. How does that correspond to x equals 1? Question mark. In other words, how many of these am I supposed to draw for each division of these? That's a question that we haven't answered yet, and that's what I'll do right now. We'll do a little bit of algebra, we'll bang it out. Okay, so let's just say the most general way to represent it would be to say that x prime is some linear combination of x and t. That's about as broad as you can get, and it's reasonable too, because look, I'm messing with both axes here. So There is one case we do know. The case we do know is, think about this. The t prime axis, this is actually x prime equals 0, and I already know what the equation of it is. It's x over v equals ct. And I also know for t prime equals 0, that's my x prime axis. And so in that case, I can say that ct equals vx for that too. Okay, so what comes next? I basically substitute those things in, and I end up with these relationships. C over D is minus V over C, V over A. And what do? I plug that back in, and now I end up with something that looks like this. Okay, now, what's the next step? So this is good news. We're making progress. I've eliminated half of my unknowns in this transformation I'm making, but I still have A and D. And this is the thing we're going to do again. We're going to say C is invariant. Notice we haven't really used that yet. We're going to use it now. And the way we're going to use it is to say that if x prime over t is c, then x over t also has to be c. In other words, the speed of light has to be measured the same in both. So what do? I divide this by this, and after some algebra, which you can look through at your leisure, you end up with a over d equals 1. In other words, a equals d. So holy smokes, this is great progress. We actually have only one undetermined thing. In other words, there's just one constant that relates these two. And now the thing to remember, which we've worked out in another video, is time dilation. Time dilation. In other words, I already know the answer. If I were to go to the frame that has the proper time, well, proper time is defined in such a way that in that frame, delta x is 0. And I already know what the answer is. It's gamma. And if it's true in this frame, it has to be true in every frame. In other words, this thing I've been writing this whole time, A, is actually gamma. So to clean all of that up, I can park that up there. Those are my Lorentz transformation equations. Now, okay, we did that work. Let's take advantage of these diagrams while we have them. A couple of things I want to point out that are interesting. Simultaneity is relative. In other words, just looking at the diagram, you don't need to do any math, although these will confirm this. You don't need to do any math. According to the x-observer, these take place on the same t line. In other words, this might be t equals 1, 2, 3, for example. But according to the moving observer, they are on completely different tick marks. So they are not simultaneous in one frame. Now, one thing to notice is that you might be interested in is, look, for the slanted axis frame, B occurs before A. That's very interesting. What if we speed up? Let's see if that changes. If we speed up, oh my gosh, that's very fast. Now we still see B is before A. And you might say, okay, well, it must be the case that no matter how fast I go, B will always be before A, except for one thing. If I switch direction, now all I'm doing is going the opposite direction. Now look, this is, I don't know, t prime equals 0, and then I draw one parallel to it up here. This might be t prime equals 1. All of a sudden, now I found that A precedes B. This is an enormous problem. I'm going to tell you why it's an enormous problem. What if the event is a person shoots a bullet, that's a terrible bullet, at another person? Event A is the person fires the bullet. Event B is the person gets hit with the bullet. What I'm saying is, depending upon how I'm moving, the person gets hit with the bullet before the bullet's fired? That's crazy. There must be something wrong with this. So let's fix this really quickly. So one way to fix it is to do this. I just move my events. And you might say, that sounds like cheating. Yeah, it is. And I'm going to explain why I cheated in just a minute. So in this case, B definitely precedes A. And let me just show you that moving the point as I did fixes this problem. If I reverse my direction, look at this. B still precedes A. In other words, the ordering has not changed by me changing directions. And that's because I cheated and I moved that A. Why did moving A matter? Well, let's think about this for a second. Let me put a C back down. These two guys are simultaneous, meaning they happen at the same instant in time. No time elapses between them. Now, think about that. If you shoot someone, how is it possible that the bullet hits the person at the instant you shoot it if the person is not located next to you? The bullet would have to have a very high velocity. A very high velocity. In fact, the velocity of the bullet would have to be greater than the speed of light, which is not allowed. Not allowed. So, to put this into more quantitative terms, what we're saying here is that your speed, another way to say this is your speed would have to be bigger. So x over t would have to be bigger than the speed of light in order to get from here to here. But for this, to get from A to B, your speed could be less than the speed of light. And so we have a name for those. Things that fall into this category are called time-like, and things that fall under this category are called space-like. Another way to say this is I can say that this quantity is greater than 0. Now notice it's more or less this, but the reason I square everything is I don't want to have to worry about what direction things are going in. If I have it guaranteed that this quantity is greater than 0, then causality will be preserved. In other words, causality is not relative for time-like events. It is relative for space-like events. And so what we say is, look, moving around had better not change causality. And so actually it turns out that there's no way to change whether or not this is greater than or equal to 0. Not only can you not change the sign of it, you actually can't change the number at all. That turns out to be another invariant. You can actually prove from looking at the Lorentz transformations that that quantity is invariant. And it's very important because, getting back to our example of the person shooting the bullet at the other person, you don't want a scenario in which just by moving, you can automatically reverse the order in which these things happen. This person gets hit, and then the other person fires the bullet. You don't want a theory that predicts that, because that's just nonsense. Okay, and so what we say is things that are space-like separated don't have a causal relationship. How could they? They can't send any signal or bullet to each other because it would have to go faster than the speed of light, which is not allowed. The Einstein equations end up giving nonsense for stuff like that. And so what we say is, if things are time-like separated and there is a possibility of causality between them, that causality will be preserved. Okay, there's loads more to talk about, but already this video is so long, so we'll just cut it off, and we'll just say, in Galilean relativity, life is pretty straightforward. Force is very important, and it's invariant, meaning we can use Hooke's law in all reference frames. I'm not saying that these invariants are true here. In fact, they're not, but we have different invariants. C is invariant. This space-time interval, so this is called the interval. This interval is invariant. Simultaneity is relative. Causality is not relative. There are loads more invariants that are useful calculationally and philosophically, but those will have to wait for another video. Hopefully this was more helpful than confusing.